you're keeping your notebook organized. And the topic, oh my gosh, look at how short, guys. You've got you got the title slide, you've got notes you're not going to write down. This is all you're going to write down today. We're going to look at 3 examples, and this is your homework. It goes fast. So guys, topic for your notes is polarity and IMFs. Don't write out intermolecular forces. We abbreviate it IMFs. So guys, here's how this is going to go. I'm going to set the stage for you by giving you sort of the bigger picture. I'll show you how we're going to do that in a minute. Then guys, we're going to dig in and we're going to learn one new thing today. And then guys, at that point, you're going to have the rest of the day to get your homework done. You guys ready to do this? Okay. So guys, in order to introduce you to the way we're going to do this, I'm going to actually look at our calendar and use this as our organizational structure. So guys, last time in class we talked about the word therefore, and we said therefore is a logical term. It basically goes like this. We have established a truth. And based on this truth, therefore, this is true, therefore, this is true. And guys, that's where we're at right now. So last time in class, we did polarity. And now we know that polar molecules have different atoms or dots. Now, guys, we're going to take the next step and we're going to say that polar molecules are sticky. They stick together. We call those IMFs. Then, guys, on Monday, you're going to find out that this stickiness causes so many things in the world that you know to be true. So, guys, let me show you an example. Actually, I'll leave them on there. Guys, this is a water molecule. It's polar. Why? Atoms or dots? These are the dots, right? These lobes are the dots. So guys, water is polar, therefore it's sticky. Therefore it's a liquid. But guys, you ready for something crazy? If water was 7% less polar, it would not stick together well enough to be a liquid at room temperature and we all would die. 7%. Guys, if water was 7% less sticky, it would not have enough attraction to stick together as a liquid at room temperature. And actually, we wouldn't die. We would have never been here because we need water to be alive. 7%, y'all. Guys, we live in a world that depends on these stickinesses, and that's what we're going to talk about. So guys, again, it goes like this. Now we know what molecules are polar, then we're going to talk about them being sticky, then we're going to talk about the so whats, and then guys, for the next 2 weeks, we're going to do labs, and that'll take us into February. Here we go. So guys, do not write down anything that comes up on this first slide. So guys, here's where we are. Last time we talked about polar bonds leading to polar molecules. Guys, we represent these polarities with arrows, and now we know that molecules that have dots are polar, and we know that molecules with different central atoms are polar. That's where we are now. Guys, today what we're going to do is this. This is the big idea for the day. We're going to talk about more polar. So guys, watch my hands. Here's what you know right now from the last homework. You got a molecule and either it's polar or it's not polar. What you're going to learn today is if it's polar, some are more polar and some are less polar. That's our goal for today. Then guys, next time we're going to talk about how this changes their behavior. But guys, today our goal is more polar. So how do we do this? This you want to write down. So guys, IMFs. Just write down IMFs. Or maybe, you know what, it's already the title of your notes. Never mind, just define it. So guys, it goes like this. Polar molecules, when they are gathered into large groups, they attract each other. They're sticky. So why are they sticky? And guys, we've talked about this, but the answer is because the positive and negative dipoles attract each other. Because you don't need to write this down again, but just bringing the thought full circle. The idea then is that this stickiness from positives and negatives attracting each other, don't write it down again, but those are the IMFs. Those are the between molecular forces. So guys, the forces of attraction between polar molecules are called IMFs. So guys, this then is the interesting bit that we're going to explore today. So guys, these attractions are very, very weak. So when you hear the word weak, your mind should be asking, weak compared to what? And guys, the answer is bonds. Intermolecular forces are about 1/10 to the 100th the strength of a covalent bond. So gang, this then leads us to ask the so what question. Well guys, check this out. You guys kind of know that this is what it looks like inside of a liquid, right? You know that you've just got molecules all jumbled together. But guys, if you don't understand this, it's fine. We're going to learn it, although you probably should. Guys, if you looked inside of liquid water, what are these molecules doing? They're not just sitting there. What are they doing? They're moving all over. Guys, it's a serious mosh pit inside of here. They are moving at hundreds of miles an hour. They're slamming into each other. They're slamming into the glass. Guys, it is violently chaotic inside of a liquid. These things are jumping all over the place. They're also moving past each other. So guys, can we make them move faster? How? Heat them up. Can we make them move slower? Cool them down. And guys, we're going to talk more about this in the coming days, but guys, the idea is this. If we get them moving fast enough, all of a sudden, they start flying out of the top of the beaker and they run off into the air. And guys, what do we call that process? Boiling. Guys, that's all boiling is taking a liquid and getting the molecules to move so fast that the forces that keep them locked in there break and they fly apart. Now guys, what are those forces that keep them in there? Intermolecular forces. But guys, here's the question. And do you guys understand this? That when water boils, the stuff that comes out the top is water molecules and not hydrogen and oxygen atoms. Do you guys understand that? That when water boils, it doesn't break into hydrogen and oxygens. It leaves as water molecules. Guys, the question is why? Why do the molecules stay together and why do they leave as individual water molecules? Guys, talk to the person next to you about that. Why do they do this? Do you guys know where that other water molecule went? I don't either. Oh, it is? Under here? Oh, shoot. Ugh. Oh, it's nasty under there. All right, guys, can we chat? You have all heard the old adage, a chain is only as strong as its weakest link. And guys, that's what's going on here. All of these molecules are all linked together by the attractions between the positive and negative dipoles. And those are weak. They are about 1/10 to 100th the strength of the bonds in the molecules. So when this breaks apart, the weakest force breaks first. And that's the intermolecular forces, and this flies apart. Guys, we're not adding enough energy to break the bonds between the hydrogen and the oxygens. Can we? Yeah, but we can't with a Bunsen burner. It takes a lot more energy than that. Do you kind of see how that goes? Okay. So guys, the question then, we'll call that evaporation. Okay, maybe not. Thanks, Soph. Thank you. All right. So guys, the question then becomes this, and we're almost done. Which one is it? Is it 10% weaker, or is it a tenth or a hundredth the strength of a covalent bond? And the answer is it depends. Depends on what? Guys, it depends on the polarity. You don't even need to write this down. We're going to show you an example in a minute. Guys, the strength of the IMFs is not the same. It depends. Depends on what? It depends on the polarity. The stronger, the more polar a molecule is, the stronger its IMFs. We're going to play with that now and we're done. You guys okay? One more thought. Guys, don't write this down, but just watch. You know that we're going to be talking about the word therefore a lot, right? Did you guys know that there's a mathematical abbreviation for therefore? Did any of you know this? It's 3 dots. So guys, in the homework, you're going to see 3 dots. It means therefore. When you are answering questions in the homework, you are welcome to use the 3 dots. It's the mathematical symbol for therefore. Okay, you ready? Do this. Guys, this is the end of our day. CH4, CH3OH, and H2O. Write those across your page. Spread them out. And then, guys, I'm going to give you the Lewis dot structures. We're going to muck around with these for a minute, and then you're going to I think you'll get all of your homework done. I did this yesterday during Short Wednesday, and some of my kids still got the homework done. So I think you guys will be good. We'll see. All right. You guys ready to go? So CH4 you've drawn before, so I'm just going to give it to you. It looks like this. But now, guys, you don't need to give this a name. Guys, in the essentials that we just did on the test, you'll notice it never said no tetrahedral, trigonal pyramid, all of that stuff. But guys, what you've got to be able to do is look at this and ask yourself, what does this look like? And guys, it looks like this. Whether you call that tetrahedral or not, this looks like that. And so, Maddox, that's actually why this is an essential, and that was the second essential. And so what we've got to be able to do is take this and realize it looks like that, and then redraw it. So, guys, what do we need to do to make this look more like this? Nothing. It's the best that we can do. So we're going to stay there. Then, guys, from there, we're going to move over to water. And guys, whether you know the names and the angles doesn't matter. You just got to be able to look at this and go, wait, those unbonded electrons bend the hydrogens down, and it literally, you don't need to draw the 3Ds, but guys, it looks like that. But now this one. This is kind of a funny little dude. Guys, CH3OH actually looks like this. Draw its Lewis dot structure. Because it actually looks like this. This is CH3OH. Well, and in a 3-dimensional structure, it looks like this, which is the same, right? You've got your CH3 and then your OH. So guys, I know you're curious people, so we can talk about this really quickly. You guys know about prohibition, right? There was that period of time where alcohol production and consumption was illegal in the United States, and the moonshine business went through the roof. People got very wealthy they called it bathtub gin. They were literally making gin in bathtubs. The problem was this. Guys, when so then and now, guys, this is actually the alcohol that gets you drunk. This is called ethanol, beer, wine, whatever else. This is the alcohol. And this is what they were trying to make in moonshine stills. The problem is that a lot of them made those moonshine stills out of wood. And the problem is that when alcohol like this, ethanol, comes into contact with wood, it actually loses one of these carbons and it gets replaced with a hydrogen, and it looks like this. This is called methanol, and it does get you drunk, but it also causes you to go blind. Do you know about that from history class? That a lot of people during Prohibition were actually losing their sight because they were drinking this bathtub gin, and it wasn't ethanol, it was methanol, and it was taking their sight. So anyway, this is methanol. It looks like so. You guys good to go? Okay. So now guys, we now need to talk about polarities. So guys, we need to figure out whether or not these molecules are polar. So guys, really quickly in your brains, remember we now have a test for polarity. It's atoms and it's dots. So guys, give yourself 5 seconds. Scan from left to right, and it's just in your brain, yes or no. Is it polar? Is it polar? Is it polar? Scanning, you should be done. Because you don't have to think about symmetry anymore. It's atoms and dots. So guys, now do this with me. Let me switch colors, which is going to freak this out. I'm going to switch to blue. All right, so going blue and coming back. There we go. All right, this should be blue. All right, so guys, CH4, is it polar? Does it have dots? Does it have different atoms around the outside? Nope, fails both tests. So guys, all we're going to do is we're going to come along here and we're going to label this non-polar. So guys, you kind of went quiet there for a minute. Please, if you don't understand that idea, stop me. So then guys, let's go over to water. Really fast. Is it polar? Yes. How do we know? Is it dots or atoms? Dots. Now guys, let's talk about this middle one because it's a little more complicated. The complication is which one is the central atom? And guys, the answer is this. If you have any central atom, the hydrogens aren't central, so it's the carbon or the oxygen. If you have any central atom that passes the dot or the different atoms test, it's polar. So again, one in the middle, is it polar? Yeah, why? The dots. Guys, these dots make it polar. You're going, wait a minute, what about the carbon and the oxygen being different? That also makes it polar. But guys, all you're trying to do right now is figure out yes or no. This is a no, this is a yes because of dots. And the minute you see that this is a yes because of dots, you don't have to think about the other rule because it already passed the dot test. Yeah. That's a brilliant question. So what about this rule that said carbon is our central atom? And the answer is so let's say that a little bit differently. Carbon is always in the middle, which means that it's central to the molecules, but it doesn't mean it's the central atom that we're going to look at. So now you're going, wait, how do we know that? And the answer is electron flows. In order to figure out which one is the central atom, we need to draw in the polarity arrows. And at that point, we're going to find out it's really not oxygen that's central. And I'll show you in just a second. But for now, all we're trying to do is identify yes or no. Is it polar? And the one on the right or the one in the middle has dots, so it's not polar, so we need to muck around. Okay, so guys, watch this then. This saves us a bunch of time. Don't do this. So now we're going to draw in polarity arrows. Polar this way, polar this way, polar this way, polar this way. Guys, that's a waste of time. You don't have to do that anymore because using our dots in different atoms rule, we know that that's non-polar, so there's no reason to draw in the arrows because we know they all cancel out because we've already identified it as non-polar without drawing the arrows. So now what about the other two? Well, guys, these we've identified as polar, and now, Maddox, this is going to be right to your question. Now we need to draw the arrows. So what do we need to know in order to draw the arrows? There you go. Oops, shoot, that really freaked out. Guys, in order to draw the arrows, we need the electronegativities, and here they are. So guys, spend about a minute and draw in all the polarity arrows. When was Prohibition? The Roaring 20s, was it the 30s? It was what? It was the 20s? Huh. Interesting. Huh. Did you guys get them? So let's pick the easy fruit first. Hold on. I was afraid of that. Just a moment. Actually, I need to zoom out anyway. All right, here we go. So I'm going to stay with blue, I hope. Oh, my poor board. Okay, here we go. So guys, let's just do this. So let's go to water first. Oxygen is stronger than hydrogen. So this is polar this way. This is polar that way. Now we've already identified the molecule is polar because of dots. So guys, which way does the overall arrow go? Up and right. So that would be up and right. And that would be the polarity of the molecule. Guys, that's the homework we graded today. This is not new. So now, guys, let's do the molecule in the middle. And Maddox, let's talk about, I want to make sure that you understand the idea, because your question's brilliant. Which one's in the middle? Check this out. So, guys, here we go. Drawing the arrows, carbon is stronger than hydrogen. So this bond is going this way. This bond is going this way. This bond is going that way. Is that okay? Now, guys, oxygen is stronger than carbon. So this bond is going this way. And then, guys, oxygen is stronger than hydrogen. So this bond is going this way. So now, guys, what is the overall flow? And it goes like this. These guys are all flowing towards the carbon, which is then flowing towards the oxygen, and then this hydrogen is flowing towards the oxygen. So guys, what we've got is in and right and up. And the overall polarity then is up and right. So guys, let me get a little hypothetical with you because Maddox asked a good question. So, and this isn't just with Maddox, but he started the conversation. So, do you see why oxygen is the central atom? Because everything's flowing in that direction. So, what would have to be true? Let me switch colors if I can. What would have to be true to make this the central atom? And the answer is this cluster right here would have to be flowing in this direction. So literally the central atom is the place where the flows, can I use the word converge, come together? It's the place where the flows come together. And in this case, the flows minus the red come together at oxygen. But if some weird reason the carbon were stronger than the oxygen, then this would flow in the other direction, and that would be our central atom. Does that make sense? Guys, that's it. But for one more thing, remember the idea for what we're going to do today is not just about nonpolar and polar. Now the question is more polar. So guys, we already know the least polar atom. It's the CH4 because it's not polar. But now guys, we got to talk about this. Which one of these molecules is more polar? So guys, do this with me. It's really simple, but do this with me. So how do we know which molecule is more polar? Here's what we do. Guys, and if you want to highlight this, it's not a bad idea. What you're doing is you're looking at the overall polarity arrow. And then you are only looking at the bonds that are right next to the overall polarity arrow. And then what you do is subtract. This is question 16 out of the last homework. You subtract their electronegativities. So 344 minus 2.2, that's 1.24. We now know the polarity of that bond. It's 1.24. Then guys, this one is also 1.24. That's worth writing down. Then guys, this. Let's go over here to this molecule, and here is our overall polarity arrow. And so now we're going to look at the neighboring bond here and the neighboring bond right there. And we do the subtractions. 3.44 minus 2.2 is 1.24. But then, guys, 3.44 minus 2.55 is 0.89. That means that this bond is less polar, making this molecule less polar. So, guys, if that doesn't make sense, add them up. This is 2.48. The overall, adding those together, it's 2.48. Here it's 2.13. Did I do that right? Why can't I do math? So this plus this, 2.13. Pretend that's right. So guys, this is the take-home message. The molecule that has the greatest total polarity around its polarity arrow is the molecule that's more polar. That's it, guys. That's what we're doing today. So guys, thoughts, questions, things you need to talk about? Let's get some homework done. Guys, grab your homework packet. Turn to page 2. Page 2 looks startlingly like this. So guys, here's the deal. When you're doing the homework, you are only going to look at the left 2 columns. Do not do the right-hand column. Don't cross it out. That's the homework. Did you notice across the top it says 2 and 3? This is 2 assignments. So guys, here's what you're going to do. For number 1, don't circle it, but the data is outside of the first 2 columns. You have to skip it. But now guys, go to number 2. This is the idea. If you have a molecule that has a low polarity, that's what the down arrow means. If the polarity is low, the intermolecular forces will also be low. Draw a down arrow. Guys, number 3, we have to skip because the data is in the right-hand column. Now guys, this. If we have a molecule that has strong intermolecular forces, these molecules will have high polarities. I think you've identified the pattern, and it's going to take you about 12 seconds to do the rest of the page. So guys, rather than do that, let's go on to page 2. And let me show you what to do on page 2, and then you'll still probably get all this done. So guys, it goes like this. On page 2, the first thing that you need to do is, guys, cross off the last 4 words of the directions. Don't explain anything. Because you don't even know the difference. We're teaching this material differently this year, and the explanations become less necessary because we've streamlined the way we teach it. So guys, here's what you're going to do. It says for each of the following molecules, compounds, draw the Lewis dot structure and figure out the polarities. Guys, that's exactly what we did on the screen just a minute ago. Then it says this, circle the more polar molecule. So how do you know which molecule is more polar? Look at the overall polarity arrow, do the subtraction for the electronegativities right next to it, whichever numbers are bigger or more polar. Get the idea? One more thing, you guys. Numbers 5 and 6. Guys, number 5, I would feel comfortable having you draw methanol. It gives you the formula. It's CH3OH. It's this. But guys, I would never feel comfortable having you draw diethyl ether. Diethyl, not methyl. Guys, that would be bad. So what I would encourage you to do is copy the Lewis dot structure out of the answers, and then figure out the arrows, figure out the polarity. Guys, same thing for acetone. Many of you know that acetone is fingernail polish remover. I would never ask you to draw its Lewis dot structure. And also propanol. I would never ask you to draw its Lewis dot structure. But given the structures, you should be able to analyze them. So guys, the rest of the time is yours. For those of you that have not yet taken the test, today after school or tomorrow after school, Flex are wonderful options. And I know that several of you haven't taken it. So only come and talk to me if today or tomorrow during Flex and after school doesn't work. Other than that, I'll be here both of those times and you're welcome to come. So guys, dig in. The answers are on the wall. Go get them.